想你们没有分，你们有分 topic 吗？应该有吧？有啦有啦，OK，这样就还好。就是说不同人的哦，OK OK OK，可以
一个那个也是同一个人。
哦，你也可以发名字在那个页数下面，那个 main topic 上面，
我会记得哦，
差不多100页是差不多。
都把每个人全部讲出来，我也不知道。现在才一点，大爷，这个是有，还在做什么？我是啥？通过已经可以通过这种这种那更比我那一波人是。兄弟，别想要学的，这个我要在这里。那准备这种我要准备什么？就是进入 presentation 开始吧，
开始录了，
没有录下来的话，我们要再讲一遍吗？
录下来就没有了。
我说没有录下，我说他没有 record 的话，我们要不要再来一遍？笔都可以用，都是有这个。
应该有，没有的话我还有。有放
已上锁。
他早上有事情哦，他下午来。
下午没有。
你下午没有来？OK，好，OK，我们待到这个结束。
来之前
，OK OK，
或者是可能早，可能就到最后一点点，有点有点
几点钟
12点多。
？10点多一点。OK。
离停所，请请出话筒。
Everyone back yet? Everyone back yet? 有没有个主在啊 ？OK，其他人在吗？ 诶，should we start? We'll take a photo first. Okay, next we have a group from Eric. Okay, so they will talk about Hilbert scheme. So we'll start with camping.
Okay, stop. I'm going to type it. I'll start it. Okay, good morning, distinguished guests, and most importantly, Dr. Ni. I am Zhou Xuekangping, and our group will be presenting to you the topic on Hilbert function, polynomial, and schemes. So, as I am the first speaker, allow me to introduce the respective subtopics my teammates will give. So I will be talking about Hilbert function and Hilbert polynomial first, and after me, Larry will be talking about schemes, and then Justin is going to be introducing about Hilbert schemes on points in the plane. After that, Eric, the leader, will be talking about irreducibility of Hilbert schemes of points, and finally, Zixian will talk about Grassmannian functor and Hilbert functor, or actually just Hilbert functor. So without further ado, let's begin with my part. So I'd like to start my part with a callback to the course name of our course, which is algebraic geometry. So what I will be introducing is a demonstration of what we can build to bridge between these two nouns, algebra and geometry. So if you can recall that not long ago did we introduce the concept of graded, where we can put this adjective to different geometric objects, such as we can say that a ring is graded when this ring can be written as a direct sum of additive subgroups. These subgroups are also closed under multiplication, and we say that an ideal is graded. We actually prove that an ideal is graded when the ideal can be written as a direct sum of this ideal intersect one of the additive subgroups. Right. And also we say a S module M is graded when this module can be written as written as the direct sum of an infinite direct sum of abelian groups, and these groups are closed under scalar multiplication of the okay, it should be S. It should be S I M J under the scalars in the ring S. Right, and we can also prove that if we quotient a graded ring by a graded ideal, what we get is also a graded ring, such that the the pieces of the graded ring also equals to the quotient by the pieces of each of the ring and ideal. Right, and with these definitions, we're going to introduce something else. We introduced what is a coordinate ring in a course about several weeks ago, that for an affine variety V in the affine space and its vanishing ideal in the polynomial ring, we define the coordinate ring as the polynomial ring quotient by its vanishing ideal. So similarly, we can define something in the projective space such that we only change the space in here from AN to PN. So it's the same thing, but we call it the homogeneous coordinate ring as such. So this homogeneous coordinate ring is also graded such that we can rewrite it as the direct sum of several of these pieces. And these are finite dimensional K vector spaces and can be considered as the K subspace spanned by the monomials in the Xi of degree K. This could come in handy when we actually calculating the Hilbert functions of certain projective varieties. And for example, we can take the now we're going to introduce what is a Hilbert function. We define a Hilbert function as the dimension of the homogeneous pieces of the homogeneous coordinate ring under the degree K. So we give out a lemma such that this simplifies how we calculate the Hilbert function in actual practice. Because what we had just now is that the homogeneous coordinate ring is a quotient ring, and in return we can show its dimension by subtracting the original ring and what we have quotient out. So this gives out the lemma. Now with these definitions and lemmas, we can play a few things around for certain projective varieties. For example, we take projective variety here to be Pn, and we calculate the Hilbert function of Pn. And so, like what we said now, we're going to calculate using the subtract lemma. So since the vanishing ideal on the projective space is the zero ideal itself, we can deduce that the homogeneous coordinate ring is just a polynomial ring over x0 to xn itself, because you're just quotienting out the zero ideal and you wouldn't make much difference. And so like what we said just now, the dimension of the homogeneous pieces just equals to the K subspace spanned by the monomials in the Xi of degree K. So what we are calculating here is only the cardinality of the span of the monomials with degree K, with degree M. So this is a simple question of combinatorics. We're just so if one looks at each of the monomials, you will find that what we are doing here is just we have n objects. We call it A1 to AN, and their total degree is n. So we're going to find how many ways we can arrange. AI has to be in bigger than 0, so it can be equal to 0, and we want to find how many ways we can arrange the AIs here. So basically, it's a combinatorial problem, and the result is you choose m objects from n plus m objects. Anyways, so we can calculate the Hilbert function here by just subtracting the dimension of the homogeneous pieces by the dimension of the vanishing ideal, because the vanishing ideal is 0, and in return we get what the result as above. Right. This is our example. superscript.
What does that superscript? The power. What does that power?
Oh, power. What I said is like so so like the space is spanned by the monomials in the xi of degree k, right? So which means here it has the, because each of these things are homogeneous, and each of the graded part of this graded ring is has the total degree of m. So because basically it's homogeneous, and it's homogeneous as the degree of m for each of for the substrate m, and its total degree is m for each of the monomials here. Right? Is that clear? So basically, if we want to calculate the the dimension of this space, it is just spanned by all the polynomials you can think of that. Okay, can I carry on? Okay, so after this example, I'm going to tell you what is a Hilbert polynomial. So the Hilbert polynomial is not actually defined, but actually it's proven to be true, such that for a projective variety, there exists a unique polynomial in Qt, such that for sufficiently large m, it stands true that the Hilbert polynomial equals to the value of the Hilbert function. So this is where I said we can build a bridge between algebra and geometry. Basically, the Hilbert function of V is defined as the dimension. So it's a geometrical language we use to describe a variety. But now we're relating it to a polynomial, which is a algebra, like not the object algebra, but the algebraic kind of language. So and we call this small h here as the Hilbert polynomial of V. Right. But like I said, this is not a definition. This is more of a theorem. We can show it's true. So this is what we're going to do for the rest of this talk. No. Right. So before that, I'm going to, but the thing is, I'm going to explain the existence of this Hilbert polynomial using a. I'm not going to use V here. I'm going to use a finite gradient module over a polynomial ring. And this polynomial ring is defined by the k over psi not to psi n. And since it is a gradient module, we're going to write it as the direct sum of these m's. They are all finite dimensional k vector spaces. So to prove this, however, we are going to use induction on n. So you will remember that n here is the substrate of the largest in the polynomial ring. And so the base case is that so the base case for this polynomial ring is that S will be equals to K, right? So in order to make that happen, n should be -1, so that there is nothing in the polynomial ring except the scalars. N. So this is our base case. And if we look at this base case, we will find that because K is just a ring, it's just a space of scalars. You can't grade it non-trivially. So all we have is K as the one of the modules. So similarly, the gradient module is the same question, and we can deduce that the Hilbert function on this is also dimensional m when m equals 0. So basically, we're not actually going to consider the case when m is equal to 0, because there is just no point. You're just considering a not graded. You're considering not graded module. So in which case we find that for all m greater or equals to 1, the Hilbert function equals to 0. And of course, 0 can be found in the polynomial. You can find a polynomial equals to 0 for in any cases. And this proves the base case. So like I said, we're going to induct on n. So we have the induction hypothesis such that there is a the n plus 1, the m is in Qm, and no, the induction is on n, but so basically the thing is that it's the same thing, right? If it's on n, the m gets level 1 more. So like this is the yeah. So basically I have to write that when induct on n, our goal is to show that on a polynomial ring with n on n plus 1 subjects is true, but like it should be like on the right side of this. It's just it might be a bit confusing, but it's correct. Right, so we're going to show this by constructing a homomorphism as such. So basically, we send an element in the module to its multiplication of by psi n. Psi n was the largest in the was the final element in the polynomial ring defined. And we call the kernel of this map as K and the co-kernel of this map as the as C. So basically, co-kernel means you are going to it basically means the codomain minus the image of the map. So and we can prove that these two things are both graded and can be written as the graded modules as these things are wrong. And anyways, so in which case we can build an exact sequence. So basically, iota is the inclusion map, and the psi n is the map we just defined, and pi is the natural projection map. So the exact sequence implies that the kernel of the right map for each of the map here, for the kernel of the right map equals to the image of the left one. So what we are going to see is that K and C here, we were proven it's just graded just now. We're going to say that they are graded as modules and can be seen as modules over K psi n, not to psi n. By saying this, we basically want to show that the hypothesis, the induction hypothesis acts on these two modules as well. Anyways, so yeah, that's what Jay says. The hypothesis inductions acts on these two modules as well. And so by definition, we can say that the Hilbert function on H minus the Hilbert function on C it equals the dimension of the of these two modules, because that's our dimension of the modules on the Hilbert function. And why does this equals to the dimension of the image of psi n? Basically, you remember psi n C is Cm plus 1 is defined as the m plus 1 portion by psi n m plus 1. M. Is that time? No. Okay. So like the definition we given just now. Oh, like the lemma we given just now. We are subtracting two dimensions that are originally the quotient, so we can their difference of the dimension also equals the difference of the quotient. So we're going to show something else, something else that also includes the dimension of the image of the psi n. So to see this, we draw a map. We draw a diagram as such, so that we show. So basically, this diagram shows that km maps to 0 and mm maps to psi n mm, and these all live in m plus 1. And why this equation stands true? That so basically you can remember that what was we learned that in linear algebra, the rank notice theorem, such that the rank plus the notice equals the dimension of the matrix. But for a map, we can also define such thing. We can also define such thing. So for a map like this, the dimension of the kernel plus the dimension of the image will also equals to the dimension of the. This is a proposition. This is a what's it? Lemma of the application of the rank notice zero. So this is a depiction of this. Also, we change the m and m to our map just now. It is stand true as this equation. So we have the following equations. What we had just now, the dimension of the image, x in here as such, and we can say because there's this dimension of the image because I n, and we discard this, and the difference of the Hilbert functions should be the same. And so we move some of the terms aside and to one side another, and we get that the difference of the Hilbert functions of m and m with m plus 1 digits and m equals to the difference of these two. And by induction hypothesis, these two can be equals to Hilbert functions, and so Hilbert polynomials, so that the difference of these also live in the polynomial ring. No, yeah. So the difference of the Hilbert functions of n also live in the polynomial ring. So basically, this is our proof. It proves that it stands true on the induction of n. It also. Yeah.
So later we leave the last.
Really? No question?
Okay, now we leave the last part later. Okay, that's what.
Okay.
站前放置。
这个给他鼓掌，他说。
Greetings. Okay. I'm Larry Contington, and now what I'm going to be talking about is basically like you can say like a very most basic introduction to like going from say pre-shifts and all the way to like schemes, and then like see how the construction basically like kind of works up. Okay. So for this one, we'll start with pre-shifts, which should hopefully be a little bit familiar. So basically, we consider mainly pre-shifts of rings, and by rings we mean commutative rings with identity. So first, we have a topological space X, and then we put a pre-shift on X. It should like consist of mainly this information, which is that we put any open subset of X ring. We just say FU here, and the elements of FU we call them sections of F over U. And for the special case U equals to X itself, aka the whole space, we call their elements the global sections of F. And secondly, for any inclusions of open sets, V subset of U, we can put a ring homomorphism from which is like reverse from FU to FV. We call them restrictions maps in the sense that like they should like satisfy like each element in FU. We denote its element to be basically like S restricted to V. And of course, restriction maps should also satisfy the following axioms. That is the ratio. If you map the empty set, it should map to the trivial ring, and the restriction should be compatible in some sense. In that, if you have W subset V subset U as such, if you restrict the FU directly to FW, it should not depend on like if you decide to directly restrict U to W, or if you decide to go restrict U to V first and then V to W. And finally, for any open set U of X, the restriction should be identity, which just means that if you restrict something from U to U itself, it ideally should not change anything. So we give a like example which should hopefully like give us an intuition of what sections and stuff those preshifts should look like. So a typical example is like continuous functions on we put consider many continuous functions. So first, R is a topological space. We can use the Euclidean topology. And thus, for any open subset U of R, we can put FU to be all functions with domain, all real value functions with domain U, such that F itself is continuous. And as for the restriction map, it's pretty straightforward. You just, if you have U subset V, then you just, it should be V subset U, sorry, my mistake. It should basically just, it should basically take any function defined on U, and it should just restrict it to the restriction in the typical function sense, which is just F restricted to V. And yes, this indeed defines the preshift in like the kind of very obvious way, which is because like if you put empty set U into V empty, there's only one function, and there's only one possible function really, so it's trivial in that case. And the restrictions of functions, like as we know, they basically indeed do satisfy the following the given axioms before. So this gives us an idea that like when we put like the rings, like we put like when we map something to like FU, what we should have the idea is that these elements are basically function like in some sense. So now with that, we consider like from pre-sheaves, we try to go to sheaves, and this pre-sheaf F is a sheaf if we need to satisfy some more nice properties, which is that for any open set U and any open cover UI, we basically have these two, which is the first is grouping, in that if you have like a family of sections that is like since a UI cover U, and then from each UI you take an element, you take a section basically, and then it has a property that they always agree, like if you take any two of them, they always agree on the intersection. Then that means that in some sense, like let's say like if they agree on like maybe say something like, yeah, like let's say like they always agree here like that, then what we should able to do is that we can glue, hence gluing. Like we should be able to glue all these functions like yeah. We should basically be able to like glue. So we obtain a new function, which is basically like if you ever restrict it, if you ever restrict it to this open subset, or we just give you this. Basically, we just glue them to get a new total function like that. And locality here, essentially it says that if the restriction is 0 for a UI, then s equals 0. But basically, if you do some bit of algebra, it's basically just saying that this gluing, the function that we obtain from gluing, it is unique. Like you basically get a unique function from gluing like this. And in this case, the continuous function pre-sheaf given just now, it's actually also a sheaf, because we know that it's basically topology that you know that if you have continuous function and they agree on the intersection, like maybe say like if you have domain and they agree on the intersection like that, then you can glue continuous functions together to make a new continuous map. Okay, so now some more terminology over here. So let's say you already have a pre-sheaf on the topological space. Then the stock of f at x is basically we consider a new ring. And this new ring basically consists of pairs. Which is one is an open neighborhood, like at x means that we consider open neighborhood of x, and we consider s to be an element on fu, which is like kind of say function, maybe like something function like basically. And then this in turn, this pair is like called a germ. And generally we mean germ, we mean that when we say germ, we mean more than like just a pair. We actually want to put like, you can check that like, we want to put equivalence on it, in the sense that like, we say these two germs, they are equivalent. If they agree on like some smaller subset, then like they agree on the intersection like somewhere, then we put them to be equivalent. And yes, you can check this is indeed an equivalence relation. And so now another thing is like we have these pre-sheaves, there's kind of like objects. And now we kind of want to consider the arrows between pre-sheaves. And a pre-sheaf, a morphism of pre-sheaves is basically like it's like we map the open set to a ring homomorphism. In the sense that like so if we map it to a corresponding ring homomorphism from FU to GU, such that for any inclusion open sets V subset U, we have this following, which is like it's like basically saying that it should like play nice with like basically this the existing like restriction maps. And in a more like category sense, this basically says that like given this diagram, it should basically commute. And so like we put that above to represent like this is the restriction map on like the pre-shift F, and this is the restriction map on like G. It basically says that like what this basically says is that like it should play nice, like they should like commute in this like yeah. And now okay. So remember that like pre-shifts are like we define them on topological spaces. So topological spaces, their morphisms are like between functions, like their continuous functions is the morphisms. And from there, we can like try to define like some new presheaves from existing presheaves and existing continuous functions. So for sheaf, for like any sheaf or presheaf, like basically on X, we can basically like define the direct image sheaf. So it's basically like we can like you have two topological spaces. Like if you already have sheaf on X, you can define a sheaf on Y to basically be like you take any open set of Y, let's say U. You take its pre-image, and since it's continuous, it's also open. Then you can put like map use this sheaf to map U to some ring, and this is the direct image sheaf. For inverse image shift, in this case, we first have a sheaf on Y, and then we want to get a sheaf on X. In this case, it's a little not as straightforward, but basically, first you take open set U of X, but this time, instead of like just a straightforward mapping, we this time actually wants to take it because like the image, continuous image of an open set need not be open. So in this case, what we do is actually take it to the ring of germs where like the open set is like contains the image of U and which is open, and this S should be in GV as well. And yeah, by germs we also means like there's the equivalence relation. And using this inverse image sheaf, we can define what is restrictions on sheaves, which is basically if Y is subset of X, then we can restrict a sheaf on X to Y. We define it to basically be the inverse image sheaf, uh, I inverse of F, which means, and I is basically a straightforward inclusion map. Okay, this one should be familiar. This is basically localization of a ring by a prime ideal. And the local ring itself is basically just a unique maximal, basically like a ring with one unique maximal ideal. And RP is one such ring, yes. So now we consider like spectrum. This is like important concept that we'll like use it to build schemes on. Okay, so first A itself, let A itself be a ring. Then the spectrum of A is basically the set of all prime ideals of A. And like if we let alpha be some ideal of A, then we can define a similar concept as like zero sets on like your in like your typical like affine zero set in classical algebraic geometry like that. In it, how do we do this? We basically define it to be a subset of spec A, where this subset consists of all the ideals that contain alpha itself. And as you can check, this with taking this specifically, taking this as your closed sets, this actually does indeed form a topology on spec A. So now we can define like a sheaf on it, spec A, which is basically you take any open subset of spec A, we map it to a ring of functions from U to, like you may notice like this. This is basically like just kind of like it's something similar to like linear algebra's direct sum, or basically disjoint union of all these like AP from P in U. And this is so that each SP is in the AP, which is and AP is just the localization of A of AP. And for any P, and not only that, it should satisfy some like kind of local property. That is that for any P in U, there is an open neighborhood V of P and there are also elements A and F in A, such that if Q in V and F is not in Q, then SQ does equals to like A over F. It does hold in AQ. Okay, now we go to like introduce this ring space. This like definition, it's basically kind of straightforward. It's basically just you have a topological space X, and you also have a sheaf of rings OX with you. A locally ring space is a ring space itself, XOX, such that the stocks themselves are like local rings, like the local rings themselves. And a morphism ring space is basically X. We have two things. We have X to Y, a continuous map, and we also have a morphism of sheaves from OY to like the direct image of F, like F S star or X like that. And a morphism of locally ring space is basically a morphism of ring space. And you have the condition that like, and the morphism sheaves, like they always like induce, you can say that they induce a morphism from each of the stocks. Like with the induced morphism, it actually also it actually is also morphism of local rings itself, which is basically just the morphism of rings, but the maximal idea of the pre-image of the maximal idea of codomain should be a subset of the maximal idea of the domain. And so if you decide to like work it out, or you can like maybe refer to Harshow or some other relevant like material, you can see that spec A is a locally ring space for any like ring A, which is basically saying that it's like spec A is like actually really nice because we are going to finally introduce a namesake of this subtopic schemes. So first we put a fine scheme. It's basically just a locally ring space, and it's isomorphic to the spectrum of some ring, basically. Basically, like it's basically spectrum. Fine scheme is a spectrum of some ring, essentially. And a scheme is basically a locally ring space that, and if you have take any, and if you're with an open cover, such that if you restrict a shift with its open cover, restriction shift like defined previously, and then it is like then the restriction is actually itself the spectrum of some rings and a fine scheme basically. And this OX is also known as the structure sheaf of X. So it's basically just saying that a scheme is like a locally ring space, and it's locally around every point. It looks like an affine scheme basically. And finally, we also briefly talk about morphism scheme. It's basically just a morphism of locally ring space, but you know that they are both schemes in space. Okay, and for some like topic that will be helpful for later, an open subscheme of a scheme is straightforward. It's basically just open subset a scheme. Like you basically just restrict the shift to the open subset. A closed subscheme is not as easy to define because we need something first, like closed immersion of schemes is basically like something like closed embed, like something like embedding, which is I. It's the homeomorphism of that onto its image, and the image and this image is a closed subset of X basically, like embedding into closed subset of X basically. And we also require that the morphism of sheaf itself is also surjective. And finally, we can define like a closed subscheme is basically an actually like equivalence class of pairs or like schemes and immersions where like they are both the same, they are both equivalent if there is like an isomorphism from Z to Z prime. such that it basically is also compatible with like f and f prime. So this last page. Yeah. Okay. 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 So like if we now let X be a graded ring, and basically we consider S plus to be the homogeneous prime ideal, consisting of all elements in S with positive degree. So and we define Proj S to be the set of all homogeneous prime ideals, and such that it does not contain all of S plus. So, and yes, it's, if you remember spec, it's very similar in some sense. Like, you basically define like the zero set of homogeneous prime ideal similarly. And we can also similarly put a sheaf on Proj S, and instead it's just that instead of AP, we just use like map it to that S0P, where S0P is a ring of elements of degree 0 in this localized ring T inverse S, where T is a set of all homogeneous elements of S that is not in T. And yes, this makes Proj S a locally ring space. And in fact, one can, if you want to, one can show that like it actually is a scheme itself. And yeah, so basically that is like how like schemes, when we say schemes, hopefully you know like what it actually means now. Yeah, that's it. Thank you. Uh, okay.
Oh yeah, right. So this Morphism ring space.
Mhm.
So why is it inducing a map into the F subscript star? What's that?
That's such great stuff. That one is like it's like it's kind of the introduced earlier. This is basically the direct image sheaf. Uh, I think that in this case, it's probably like so that like the morphism of sheaf like this is like more natural in some sense. Because like let's see this. Because like we have something like from we have a sheaf or Y, and it itself is like it itself is like something attached to uh Y. So like using this I think so that it's probably like so that like it maps it more naturally because like the direct image is like also like mapped from X to it's like you're given X to Y like the sheaf like mhm, yeah. Mhm,
Thank you.
mhm.
So I start. Okay. So welcome everyone. Wait, on that, on that, on that. Okay, so welcome everyone to my part where I introduce the concept of Hilbert schemes of points in the plan. And meanwhile, you can play a little game as to guess at which page I would end my presentation. And we begin by consider a motivating questions. That is, how do we understand or describe a collection of endpoints? In particular, the space of all configuration of endpoints in the plan, or more precisely, in the affine plan. If the points are all distinct, then we have an unordered set of n locations of where we could place our endpoints. But the problem arises when we have collisions of points. Suppose we have 2 points, P1 and P2, moving closer and closer until they merge into a single point P, so that our set becomes as shown. Then the issue is that we have lost information. We know the 2 points are at the same location, but we have forgotten how they came together. For instance, did they approach along the x-axis, the y-axis, or some other directions, for example, along a line? What we want is that a parameter space to capture all of these configurations, including like how do they collide. And a good parameter space should not lose this kind of information. And before we proceed, let's look at the definitions of the Hilbert schemes, which is defined as the set of ideals subject to the condition that the dimensions of the corresponding quotient as a vector space equals to n, which is the numbers of points we would like to describe. A particular question is asked, why do we consider ideals and why do we consider the dimensions of the quotient? And so to give an answer or to motivate the definitions of the Hilbert schemes, we proceed with the question we posed at the beginning. The most intuitive way to create a space of n unordered points is the construction of a symmetry product, which is defined as the quotients of n copies of the affine planes by the actions of the symmetry groups, which just permutes the point. For example, when n equals to 3, we have this kind of elements living inside the symmetry product. Nevertheless, this space has problems where collisions of points happen. It is singular at the points of collision. We will explain in details what do we mean by singularity here, but the essence for now is as follows. Consider 2 distinct points, P1, the origin, and P2, let's say T0. If we let T approaches to zeros, then the limit is a double point at the origin, or the fat points at the origin. But how should we describe this double point? Did the points collide along the x-axis? Or what if P2 is equal to 0t and they collided along the y-axis? Or along the line y equals to x when the points are P2, when the points for P2 is tt. The symmetry product just see the results as a set of these unordered tuples. And it loses the information about infinitesimal it loses all the infinitesimal information about the directions of approach. And this is what sort of make it singular. And so we need a better space to keep track of this extra data. And the Hilbert scheme is a refined object that does this job. So let's see how we can motivate that definition. Consider a single point whose whose corresponding maximum ideals is the one shown. Then we know that there's this isomorphism, which as a vector space is of dimension 1. Now suppose you have n distinct points, and suppose we have n distinct points, and the corresponding ideals vanishing at all of these n distinct points is the intersections of all the maximum ideals corresponding to each of these distinct points. Applying the Chinese remainder theorems gives us these isomorphisms, and which is in which this quotient is indeed n-dimensional vector space. And we call these dimensions of the quotients the co-lengths of the ideal. Now let's see what happens when the points are not distinct, and we want to describe a point that has some thickness or multiplicities, particular when collision happens. Now consider the ideals I naught, which represents single points at the origin, with which the corresponding quotient has dimension 1. Consider another ideal Ix generated by x squared and y, whose zero set is also the origin, but the ideals are different, and this ideal has co-length 2. Particular, the ideal knows that the point should be counted as 2 in some sense. And this is an example of a fat point. It's like a point that also remembers a bit of thickness or the tangent directions. In this case, it is thickened in the x-axis. On the other hand, if you consider the ideals Iy generated by x and y squared, whose zero set is again the origin, again is a different ideal, again is of co-length 2. But now these ideals represents a double point thickened in the y-axis. Now these different examples or these different ideals allow us to distinguish between the different ways points can collide, and resolving the issue we had with the symmetry product. And I hope this sort of motivates the definition of the Hilbert schemes. Now let's see some more examples when we have one point by the Hilbert now Stellensatz, saying that there is a bijection between points in the affine plane and the maximum ideals of the polynomial ring. In other words, in particular, the set of all ideals of co-length 1 is geometrically identical to the set of all points in the affine plane. Now, when we have 3 points, suppose that we have a double point at the origin and a distinct point P2. The corresponding ideals for the origin is I1 generated by x squared and y, and suppose, and I2 x minus 1 and y. And the ideals for the combined configuration is their intersections, and in this case, this ideal is of co-length 3. On the other hand, suppose we have a triplet origin, and one possible ideal is generated by x squared equals to x cubed and y, and this represents a point, collisions along the x-axis. And for the second one, represents collisions along a parabola y equals to x squared. Now here we list some of the fundamental or important properties of the Hilbert schemes proven by Fogatti in 1968, which says that the Hilbert schemes of points is a variety that is smooth, connected, irreducible, and of 2n dimension. Our next presenter is going to talk about some of these properties in details. So, yep. And now we would like to see an application of the Hilbert scheme of points in the plane. So far, we have 2 spaces, namely the simple but singular symmetry. Okay, the singular product, the singular symmetry product, and the more complex but smooth Hilbert schemes. The upshot is that the Hilbert scheme of plane, the Hilbert scheme of points, is a resolution of singularities. Now, to discuss why this is true, we need some preliminaries. Now, first we settle the singularity of the symmetric product. We call that a point of a variety is smooth if the dimension of the tangent space at that point equals the dimension of the variety. And if it is not smooth, it is said to be singular. So to show that our symmetric product is singular, in other words, it contains at least one singular point, it is enough to just identify a singular point, and to identify a singular point is equivalent to show that the dimension of the tangent space at that particular point is larger than the dimension of the variety. Now, for our symmetric product, it is defined as the n copies of the affine planes, which has dimension 2n. But since the symmetric product is defined as that variety acted on by a finite group, the dimension is not being affected. Particularly, the symmetric product also has dimension 2n. Now, for simplicity, we consider the case n equals to 2. Now, first of all, the coordinate rings for the two copies of the affine planes is this polynomial rings with 4 variables, and the coordinate rings for the symmetric product is the polynomial rings consisting of invariant polynomials that is generated by 5 symmetric polynomials. And these 5 symmetric polynomials sort of embed our symmetric product into A5 with coordinate as shown. And as we know that the tangent space of a point of interest is defined based on polynomials which vanishes at this particular point of interest. So our goal is to find a defining polynomial equation, a defining polynomial. One checks that this is a valid relations, and we can define our polynomials in terms of this relation. And then we record that in our case, the dimensions of the tangent space is equal to 5, which is the dimensions of A5 minus the rank of the Jacobian matrix. So our goal is to just identify a singular point. And the easiest point to test on is the origin. If we test on the origin, then the rank of the Jacobian matrix is 0. You just let x1, x2, y1, y2 all equal to 0, and then you will see that the partial derivative of the polynomials are all 0, and the rank is 0. And in this case, the dimensions of the tangent space is larger than that of the symmetric product. In other words, the origins is singular. But we want to do more. We would like to identify all, if possible, the singular points of the symmetric product. So we work backward. We know that singular points are what make the partial derivatives either at that point or equal to 0. So working backward, setting the partial derivative equal to 0, solving the equations, we see that the singular point should be one such that it represents a double point. In other words, all the smooth points of symmetric products in the case when n equals to 2 corresponds to distinct points. More generally, we have this result. The symmetric product is singular at points where 2 or more coordinates coincide, and the smooth points correspond to the distinct points. So we have identified that the symmetric product is singular. So let's see how the Hilbert schemes can resolve these singularities. And to do so, given an ideal, we would like to produce an element in the symmetric product. And since the ideals must have column n assumptions, the points it corresponds to must be finite. And recall that the Chinese remainder theorem says that we have this isomorphism, where IPI is the ideal corresponds to that particular distinct point. And this allows us to, because the isomorphism is an isomorphism of vector spaces, this allows us to define the multiplicity of each distinct point as the dimensions of the corresponding quotient. And in this case, we can define a map called the Hilbert-Child map that sends the ideals to the set of points where each point is included with its multiplicity. So for example, suppose n equals to 2, if the ideals I corresponds to two distinct points, then each of the points must have multiplicity 1, and that the map returns the multi-set of distinct points. And when the ideal is corresponds to a double point, then the map returns a multi-set of double points. Okay, so we would like to see how is the resolution of singularities happens. So first of all, for the case of the smooth points, which corresponds to distinct points, the fibers of these smooth points corresponds to only one ideal, as we have shown previously, which is just the intersections of the maximal ideals corresponding with each of these distinct points. Particularly, the Hilbert-Charles map is an isomorphism over all the smooth points. But what about the singular points? Consider a singular point Q, which represents a double point. Then the fibers of these points is the ideal, which is the ideal subject to these subset inclusions, where the right inclusion is obvious. The left inclusion is to ensure that the dimension, the core length of the ideal does not exceed 2. And then we have, by the correspondence theorems from algebra, that the two sets shown are in a bijection. In particular, finding our ideal I is exactly the same problem as finding a one-dimensional subspace inside a two-dimensional vector space. M mod out M squared is a two-dimensional vector space. But the geometric object that parameterizes all the one-dimensional subspaces of a two-dimensional vector space is precisely the projective line. And this is how the Hilbert schemes resolve the singularities by corresponding to a unit, by corresponding double points to a unique line representing a unique directions of collision. So for example, at the point's origin, you can say we can view that the ideal I, the first ideal I corresponds to collisions along the y-axis. The second ideal corresponds to collisions along the lines y equals to lambda x. Overall, the Hilbert-Charles map is a resolution of singularities. In other words, it is a birational morphism of the and that the Hilbert scheme of points is the blowout of the symmetry product. And so, as a summary, we begin by asking how do we describe a set of collections of points, and then we pose one possible options is the symmetry product, and then we see that these things does not work, does not give us a good, does not act as a good parameter space we want. And then we seek for an alternative solutions, in other words, the Hilbert schemes, and find out that this is a desired result. And that concludes my part. Thank you.
Where you get the reference?
This one. There's no reference for the examples.
I mean the collision.
Insight from AI, details I fill out. Yeah. Yeah.
All these things also. It's not by AI, it's by some other person, but they didn't fill out the detail. Yeah, I guess that's the reason why physicists start to look at Hilbert scheme, because exactly they are describing how the particular line and the algebraic information. Yeah, so that's why this is on the hot topic now, Hilbert scheme, because it is related to point collision.
Really.
And Yeah, so can I go back one slide? Yeah. So the pair, the example 1, 2 there is just one, like two of the examples that you provide now.
I think there are more.
There should be more.
There should be more. These are just some examples.
And then another question is, dot collision along y equals to y lambda x. Does it matter I change s squared to x?
If you change
X squared to x?
this to x,
Yeah.
then we have to check if it satisfies the correct.
That's what?
If the quotient, if you change this to x, then you have to check if the dimension of the quotient is 2. If it is not 2, then it does not work.
So I mean, like, let's say, so cube 1 and cube 2, what's the difference?
Cube is 1 and 2. Or 1 is squared 1 point, 1 is squared. 1 is about 1 point only, 1 is about 2 points. So as we have shown there just now, for 1 point, because you only have one distinct point, and the Hilbert sentence just says that the Hilbert schemes of 1 point is in a bijection with the affine plane, and pretty much there is nothing to.
So cube 1 is always smooth.
Cube n of affine plane is always smooth.
If what?
Cube n of the affine plane is always smooth. Doesn't matter 1, 2, 3, or 4.
Sorry. Oh, yeah. Sure. I mean, like, oh, yeah. Sure. I mean, like, sim 1,
Sim 1. I think should be smooth because there's no collision here.
But all these things you have detail inside your.
Yep.
Okay. Thank you.
Okay, hello everyone. Thank you, Justin, for introducing Hilbert's scheme for us. And my part is quite related to his part, and I'm continue to talk about irreducibility of Hilbert's scheme of points. And first, I want to introduce this. Okay, first I want to introduce this topic in a very tricky way. So, what is Hilbert's scheme? The precise definition in Harshon's book, I put it here. And Harshion says that Hilbert's scheme is a scheme which parameterizes all closed subschemes of Pn, which I don't think you understand this sentence, so did I. And my part today is actually try to say that this definition is a general definition of Hilbert scheme, but me and Justin, we just talk about the Hilbert scheme of a fine space, and Justin just talk about the Hilbert scheme of a fine plane, and we can generalization the definition of it, and says that let K be an algebraic closed field, and n is a natural number. The Hilbert scheme of n points in AK in AD denoted by Hilbert, n AD is defined as a set that the ideas in the polynomial ring with d variables and either idea such that the dimension of K and the polynomial ring quotient by the idea is equals to n, and we also denote it as HND. And actually, how is this related to the last page, the scheme definition? And actually, it says that the Hilbert scheme parameterizes the closed scheme, right? And Larry just introduced what is a closed scheme. And actually, later, Ziqian will talk about that such that a length n closed subscheme of AD, actually there is a bijective correspondence to the ideas I in the polynomial ring, such that the dimension of the AD quotient by I is equals to n. And this helps us to reduce the general case of Hilbert scheme to just the set of idea definition. And let's see some example of Hilbert scheme. For a very simple case that Hilbert scheme of n points in A1 is just bijective to AN, because by definition that Hilbert scheme of n points in A1 is just the ideas in Kx such that the dimension of Kx over I is equals to n.
And we know that Kx is a principal ideal domain, so the ideals in it must be a principal ideal. And from AA1, we know that it's generated by the unique monic polynomial with the lowest degree in it. And we call it I equals to ideal generated by a polynomial f, and then the quotient ring has a dimensional n if and only if f is a monic polynomial with degree m. And so if we write f equals to a0 plus a1 x2 x to the power of n, then it will correspond to a point a0 to it should be n minus 1 in an. And we can see that actually not every ideal in the polynomial ring will lives in a Hilbert scheme because lives in a Hilbert scheme of points, because we know that it should satisfy the dimension of the polynomial ring quotient. The ideal will be a finite number. For example, the ideal x squared y z cube lives in A3 is an element of Hilbert scheme of 4 points of A3, as the A3 quotient I1 is spanned by 1x, z, and z squared, but the ideal y minus x squared lives in A2 does not live in any Hilbert scheme of A2, because the quotient, if we quotient the polynomial ring over that ideal, it is isomorphic to Kx, which is not a finite dimensional vector space over K. And after that, later we will see the irreducibility of the Hilbert scheme. And actually, this is a quite historical problem. As Justin mentioned, in 1968, Fogatti proves that Hilbert scheme of n points in A2 is irreducible, while its smoothable component is its only component. And it's proved by Antonio that a Hilbert scheme of n points in AD is irreducible when d greater than or equals to 3 and n sufficiently large. And he also proved that when d equals to 3 and n greater than or equals to 78, the Hilbert scheme is reducible. Actually, later we will see an example that the proofs of Hilbert scheme of 102 points in A3 is reducible. And later in 1980, Mazzala proved that Hilbert scheme of n points is reducible when n is irreducible when n is less than or equal to 7. And later in 2008, these 4 people, they proved that Hilbert scheme of 8 points in A4 has 2 irreducible components, which means it is reducible, right? So we can see that for 8 points, it's the simplest case that a Hilbert scheme can be reducible. And we will talk about the reducibility by Hilbert-Cho morphism, which Justin also introduced earlier. And we can recall the definition that a symmetric product sim nx is x to the power of n quotient by Sn. Here Sn is the symmetric. It acts by permuting the coordinates. And the topology defined on it is the quotient topology induced by the canonic map, which sends every element in Xn to its corresponding equivalence class. And which means that if V in sim n X is open, means that its preimage is open in Xn. And Justin just used multi-set way to express the element in sim nx, and I try to use formal sum way to prove it, because we know that when we say sum, the addition is abelian, right? So we use this way to mean that the order does not matter in this symmetry product. And we define the locus U in sim ns is a subset that all points are distinctive. That means that it's P1 plus 2Pn such that Pi not equals to Pj for all I not equals to J. And we claim that U is open in sim nx. And actually, I think this is quite trivial, because just consider its preimage, which is a point in Xn, and Xi not equals to Xj for all I not equals to J. And then its complement is union of all diagonal, which is this thing x1, x2, xn, such that xi equals to xj. And it can be seen that it is the zero set of xi minus xj, so it is closed, and the finite union should also be closed, and hence V is open. And actually, as Justin mentioned, we can actually view Hilbert homomorphism as a blow up of the sim nx on these diagonal terms. And V is preimage of U, so U is also open. And we define the Hilbert homomorphism as this map. Actually, I think Justin expressed the multiplicity of I quite well, and I can give another example to see this. Just consider an idea that it's x y minus 1 and the y square y minus 1, sorry, this no comma here, and the x minus 1 and x minus 1 y square. And I think we can use a way called Gardner basis, which I will not introduce here, to show that this is a union of two ideas. One is x y square and one is, sorry, and one is x minus 1, y minus 1. And this will correspond to 2 points. It's zero set. It's 0, 0, and 1, 1. And we can check that the 0, 0 here have 2 times it comes. And the 1, 1 is just 1 time. So if we do this to Hilbert homomorphism, we show that the pi of this is actually 2, 0, 0 plus 1, 1. Okay. Actually, you can see that, and my way is to show that this will equal to an intersection of the ideas. And if you portion this idea, you can see that I think what you are saying is right, but this 2 is actually this ideal quotient by the polynomial ring has a dimension 2. Yeah, that's my definition of the
Coordinate.
It's coordinate ring dimension over the field. Yeah. Dimension of the, yeah. And here is a proposition that.
So meaning the Hilbert scheme can be traced as a multiplicity of ideal that is equal.
Yeah. Okay. And the Hilbert and sorry, I forgot to mention that the Hilbert homomorphism Justin already explained why this thing should live in the sim NAD, right? Because it can be expressed as isomorphic to a product of the ideal quotient, product by the polynomial ring quotient of the ideal, right? And so, yeah. And the Hilbert homomorphism is isomorphism over the locus U, and where all points are distinct, I already explained. And it follows that the preimage of U is open in Hilbert of AD, and in particular is dense in its irreducible component. And I will not prove this, but I think a sketch is that we mentioned earlier that pi is actually, you can view as a blow up over the diagonal terms, so it should be continuous, and so the continuous of preimage of open set is also open. And we call this preimage of U the smooth locus, and we call its closure the smoothable locus. And here is a proposition says that the smooth locus is smooth of dimension ND, and I think this is easy to understand because the sim and because the Hilbert scheme because the smooth locus has the same dimension with the symmetric product, and the symmetric product is AD to the power of n, right? Also, we quotient by the permutation group, but the symmetric group actually just do the permutation. It did not reduce the dimension. And the smoothable locus is an irreducible component of the Hilbert scheme, and it follows that the Hilbert scheme is irreducible if and only if it equals to its smoothable locus. And then we can show that actually the Hilbert scheme of endpoints in A2 is smoothable and irreducible. And we can see a proof sketch here. And actually this proof does not use the Hilbert homomorphism. And later we will see Hilbert homomorphism to show that a Hilbert scheme is reducible. And we can see that a proof sketch such that we use mathematical induction to prove this statement. And when n equals to 1, we already show that the Hilbert scheme of 1 point of A2 is bijective to A2. And because any idea in Hilbert scheme of one point in A2, it should must be a maximal idea, and which is given by the form x minus a, y minus b, and by Hilbert non-standard cells, it corresponds to a point AB in A2 bijective B. And then we define Hilbert n plus 1 by become a subset of Hilbert scheme of n points product Hilbert scheme of n plus 1 point, and it should follow that the ideal I1 will be a subset of I2. And actually, you can check that after that, our projection should be surjective, and yeah, the phi and the psi is just its projection back to Hilbert scheme of n points and Hilbert scheme of n plus 1 points. And then we define a morphism rho such that it sends this Hilbert n plus 1 to A2, which sends a pair of I1, I2 to be a point that I1, I2 differ. And actually, we can do this because I1 and I2 lives in different Hilbert schemes, so they cannot be the same because the quotient dimension should be different, right? And then the whole proof you can see in Hilbert scheme of points on surfaces by this Pedro's article, and shows that a map big phi, which defined as phi cross rho, it sends the Hilbert n plus 1 to Hilbert n A2 cross A2. And you can show that the fibers of this map, the fiber means the pre-image of 1 point, and should projective space. And since this big phi is a surjective morphism with connected fibers onto a connected space, then this shows that the Hilbert n plus 1 itself is connected, and the projection is surjective and continuous. So Hilbert scheme of n plus 1 A2 is also connected too. And use mathematical induction, we prove that any point of Hilbert scheme over A2 is connected, and we know that connected implies irreducible, right? Because the connected thing also asks for a disjoint, but the irreducible does not. And other than that, the definition are the same. So it's connected is stronger. And then we will use Hilbert, the conclusion we just say about from Hilbert Joe to show that the Hilbert scheme of 102 points in A3 is reducible. And to fulfill this proof, we first define what is a Grassmannian. A Grassmannian GKV, while V is a vector space, is a set of all k-dimensional subspaces of V. And as we mentioned, the smooth locus has dimension ND in Hilbert scheme of n points over AD. So this Hilbert of 102 points A3 should have a dimension of smooth locus 306. And as we mentioned, if it is irreducible, then the smoothable component is only component. So it should have dimension of 306. And our goal is try to create a family of distinct elements, which is ideas in Hilbert 102 A3, such that its dimension is greater than 306. And this will implies that not all elements in that are smoothable. So the Hilbert scheme is reducible. And note that the space of S7, notice that this S7 is not the symmetric group we mentioned earlier. This S7 denotes for degree 7 homogeneous polynomials in 3 variables. And I think it is also another combinatorics question. What is the dimension of this S7? And we know that it should be 9 to equals to 36, right? We just to try to compute that put x, y, z here and a, b, c such that a plus b equals to 7. And this is a combinatorics question, so the answer is 36. And we create a family that parametrized by the Grassmannian of 18 dimension. Here, parametrized means that we create a map from the Grassmannian to the Hilbert scheme, and we send every element in the Grassmannian, which is a subspace of S7 with dimension 18. And we send it to the idea generated by V and the polynomials with degree 8. So yeah, so the V contains many polynomials of degree 7 because it is a subspace, right? And we need to check that the image of this map actually lives in our Hilbert scheme. So we need to check the the polynomial ring quotient by the idea here will have length, will have dimension 102, right? And here the length, just I mentioned the length of some closed subscheme is just the dimension of the ideal. Yeah, so we compute that if we quotient this ideal here, we quotient every idea with degree 8 or more than 8. So we just compute how was the dimension below 8. And below that, we computed here the 136 things. I explained that this is just the dimension of 0, the 0 time, because the 1 is the dimension just k, and here the 3 is the subspace contained in just a joint one variable. Sorry, the variable with degree 1, which is x, y, z. So maybe the 6 here contains element like x squared, y squared, these things. So after that, we computed because the degree the monomial with degree lower than 7, we did not quotient it, so we need to add all of their dimension together. But later in the 7 dimension degree 7 case, the total should be 36, but we quotient 18 of them, so it's left for 18, and we figure out that this sum is just equals to 102. So we show that the image of this map is actually lives in the Hilbert scheme of 102 points. And later then we compute the dimension of the Grassmannian. The Grassmannian, how to compute this? Because you see that this matrix has 36 columns, which correspond to the S7 has 36 dimensions, and we just fix 18 of them. The left elements, they are free variables, and the dimension of this Grassmannian should be 18 times 18 is 324, which is greater than 306. So we show that the Hilbert scheme of 102 points actually have a subset that has dimension greater than 306. This proves that the Hilbert scheme is reducible. And after that, I will try to introduce a definition of multigraded Hilbert scheme, but I will not explain in details. It's just that what is matter here is actually this multigraded Hilbert scheme is correspondent to a degree function. We call it here the grading D, and actually this degree function, if we just send every element to 0, should be the simplest case that the Hilbert scheme of endpoints in AD. I will not explain this in details. And if we let it to be a summable function, and it will correspond to a Hilbert function. And I mentioned this is not I trying to explain this, but I just try to say the last theorem. As I mentioned that the Hilbert scheme of 8 points, I think earlier we mentioned this is actually proved by this Dustin and Daniel and Velasco and this 4 person shows my last theorem and says that the Hilbert scheme of 8 points over A4, it has 2 irreducible components. One is, as I mentioned, the smoothable component of dimensional AD, and the other one is actually in a form of graded Hilbert scheme, and it is denoted by G8D of dimension AD minus 7, which consists of a local algebras isomorphic to homogeneous algebras with Hilbert function 1, 4, 3. This means other term is 0. And actually, I'm not quite figure out what this means, and I think this will be my later research parts. Hopefully that I can finish this in my report. Okay, that is all my part here today. Thank you.
How do you see Hilbert scheme as a blow up?
Sorry, as I mentioned, I haven't quite figured out this problem.
Blow up.
Yeah, the blow up. Do you have other questions? Okay, thank you.
So I'm going to explain what is Hilbert function, and then we have a more abstract definition on the Hilbert function, and then we go to a more abstract Hilbert scheme definition. Then we will explain how this general definition of Hilbert scheme goes to the endpoint Hilbert scheme. So Hilbert functor is a map from the category of scheme to the category of the set, which every element should be flat. So we have to explain what is flat. So a flat morphism is defined on a map of the R module such that if we have very injective R module morphisms, then the F injective F tensor with the identity on the M is also injective. Then we say this F map to the F tensor identity on M is a flat morphism. And then we say the M is a flat module, or we say M is flat over R, which will use it a lot in the after that.
Typo then.
No, it maps every injective morphism. It will still be injective after we tensor with the identity on M.
You bring jacket.
Yes, it should be injective, yes. Then we have some proposition on the flat morphism. So basically, if M is flat, we don't need to check every we don't need to check every injective map. We can just check for every finally generated ideal P. Then if the tensor map to the M is injective, then the M is flat. Also, we have the I think there is if we have a flat M and a ring homomorphism, then actually M tensor S is a flat S module. Of course, this flatness is also transitive. Sorry. So if we have A is flat R module and B is flat M module, then B is also flat over R. Also, the flatness is, we can work the flatness on the short exact sequence, but it is kind of not reversible. But if we have B is flat, then the A and C actually both flat. And if the B and C are both flat, then A is actually flat. Then we come to the definition of Hilbert functor. Hilbert functor maps from the category of scheme to the category of set. Then if you give me a scheme, we give you a set of all the set flat over S. But this set is actually in the product of Y cross S. In the further discussion, we don't view this as the cross product. You can think it as a map from the Y to the S. Then we can fix some subset from the S. Then we say the set fixing the subset S is actually a fiber of the S naught. This also we can take a remark that this Z is actually a closed subscheme. It is if it is flat over S. S is a scheme. It comes from the category of the scheme. Yes, we need to fix a projective variety for this definition. Then we have a proposition for but this is not actually used in other theorems, so we go fast. Then we need to give a new definition before we go to the next theorem. So we say what is representable functor. Representable is actually you can imagine what it happened. That is, we have a functor that is representable by an object. That means if I give you an object, then you know what this functor actually do by some connection. Then we need to explain it in the word of category. That is, if this functor is representable by X, then actually the functor is isomorphic to the group of homomorphism from something to the X. Then actually, if the functor is representable by an object, then the object is actually unique up to isomorphism. We can check the commutative graph below. The left-hand side and right-hand side is two elements in the homomorphism group. Then actually, G inverse compose F is actually isomorphism from the X1 to X2. That means it should be unique, but not everything is representable. Then we come to the Hart theorem proven by Grothendieck. Hilbert functor is actually representable by a projective scheme over the integer. So actually this scheme, we call it is the Hilbert scheme. That is why we are interested in the Hilbert functor, because it gives a unique scheme, unique projective scheme becomes the Hilbert scheme. So actually the functor is, if you give me a scheme, then I can give you a Hilbert scheme. I map every scheme to the Hilbert scheme. So that means we have a universal object that can represent all the Hilbert scheme in the fixed projective variety. Here we have the P is actually the Hilbert polynomial. So because from the definition of the representability, so if we have any other Hilbert scheme, then we have a unique morphism that classify the Hilbert scheme by this F tensor identity star. The star is wrong place. Furthermore, if the Hilbert polynomial is constant for a large M, then we get actually the
Hilbert scheme becomes the Hilbert scheme of endpoints. In this case, because the Hilbert polynomial is constant, then actually we get a zero-dimensional closed subscheme. Then I didn't really prepare the slide, but I have to explain another definition given by Eric, that Hilbert scheme is actually the set of ideals which the dimension of the affine space over the ideal is actually n. But actually, like what we remark, the Z is actually a closed subscheme if it is flat over a scheme. If actually Husson also have a theorem that if we have a scheme which is we have an integral scheme, which means that every shift is integral domain, then the scheme is then the Z is flat if and only if every I forgot it. I forgot. Ready done?
Okay, so the other group member can come together. Would you write the proof, or I mean, like, not proof equivalence, but proof that the Hilbert scheme given by the ideal definition is the same as the Hilbert scheme given by the subscheme definition, and then show that it satisfies these flat property here. Will you do that in your project?
Yes.
Okay.
Okay.
Yeah, please do it. Yeah, the thing you forgot. Okay, any question for their group? Some of you want to leave already. Any question for them? Yeah.
Like this as close. Yeah, it forms a topological space.
Yeah.
It doesn't mention topological stuff for space.
哦，这是 topological space 这是跟 set in it。对，就是有开机关，有开一个
Open set in the spec.
Yeah, just complement of the. Yeah, just complement of the zero set.
So the complement of the prime ideals and the spectrum of A forms an open set in the topological space.
Lives. Did you repeat it?
I don't quite understand how the spectrum of A and forms a topological space. So what is the open set or closed sets in it, or can you give an example?
Okay, so like exactly it's just like online
I think on his writing, I can go back to the slide. I think there is some. Okay, you can continue writing. I think I can help you to find the slides. Well, sorry, go on. Yeah, this. Yes, actually, there are here that alpha is the idea in what we find is you can kind of another kind of zero set that is modern way to see a zero set, and this defines as the prime idea in spec is beta in spec is and alpha lives in beta. We call this set of idea in prime idea in spec is the real set of the idea alpha. Actually, according to my reading, and this alpha thing can not just be an idea but also a point on a set. But and then that the B alpha, we define it as the stack in the base. Yeah. So the complement should be open.
So to extend on this question, so let's say A is a polynomial ring to n variables. And then does the topology on this flat space actually transfer to AF? The apply
I think
Because it's science topology.
yeah,
that is the normal science.
I really the heat transfer.
I think transfer on this to based on
You say that open set here correspond to open set here.
Because there is key topology defined in the polynomial. So what if we are not a polynomial ring? Then it becomes the prime idea sense.
Yeah.
I think to answer your question, according to my understanding, that this is not bijectively correspondence because the points in Kn is just correspondent to the maximum ideal. But if we consider the prime ideal, but I think it doesn't matter because according to my understanding, prime ideal is just corresponding to the how do you say ephemeral IP.
Hello, testing. Okay, I also get something to say on this thing here. So, basically, this V alpha here will satisfy the closed set property that define the topological space. So you show the like Zariski topology, basically the thing that defines this V alpha, this subset inclusion here. And then if you like, you can take A to be, let's say, KT, K adjoint T. Okay, spec of KT supposedly is a bunch of prime ideals here. Actually, you can see that with that topology, and you can build a isomorphism to K. I mean, like if you look at the prime ideal in KT, I think basically it's just maximal ideal there. So it's the same thing. So the maximal ideal will correspond to the point that it defines. So you have one point with a prime ideal, one point with a prime ideal. Then you form spec KT isomorphic to TK. Right. Okay. If no question, let's take a group photo first before some of you want to leave. Right. Let's take a group photo and then you guys can take a photo later.
Okay.
Yeah, with your slide. Yeah. Can you take a photo? Maybe just sit there, no need to move. Yeah, just sit there, then no need to move. Yeah, just sit at your own seat. Okay. Yeah. Hey, Rachel, want to take photo or not? You want to take photo? You want to go into a photo? You want to go into a photo? You want to take photo? Huh? You take photo? Tina want to join a photo? Or you join a photo? You want to take photo?
看得到我学校做的密律。
还是拍得到。对，所以来了，3, 2, 1, algebraic geometry. Hilbert.
So yeah, so I think we get a lunch break now. Break until 2 o'clock. We'll come back at 2. Start at 2. Yeah. Yeah. So if you want, we can go lunch together. Okay. Yeah, after they take their photo. Yeah. 你们要跟你们的 slide 一起照啊。
就放到毕业吧，我们。
Yes. Okay. Okay. 去对面。
是。
问他们这样。
解锁
我们要去面对面嘛。东西可以放这边嘛哈。如果你不怕的话，你可以放这里。怕的话你就带走。我东西可能会带走。
那我带走，可能不回来。
你不回来？
下午是考博士要来吗？
要。
刚刚早上都没来啊。
他们就没来哦。你要像他们的话就
OK，我考虑一下。
反正是compulsory就对了。